Welcome to video 3 for our lecture series on Wednesday, March 1st. We're going to discuss how to draw some very simple Lewis dot structures for atoms, monoatomic or single atom ions, and then some basics of our ionic compounds. Now, the driving force behind drawing any Lewis dot structure is that we need to know the number of valence electrons that we can find on each element. So I'm going to pull up in a periodic table. And we are going to remind ourselves of the valence electron configuration, and thus the total number of valence electrons in each of our main group elements. So in group 1A, we are always going to have valence configuration NS1, which means we always have one valence electron, which is also the explanation as to why these things tend to form +1 cations. They want to get rid of that valence electron so that if they do, like let's say sodium, its electron configuration would be the same thing as its preceding noble gas, which is stable, has octet, which is neon. So we know that there is one valence electron in any of our group 1A elements. Group 2 always has the valence configuration NS2, so these always have two valence electrons. Okay, main group 3, these always have a valence configuration of NS2NP1. So if I were to count these in sum, that'd be 2 in my last filled S and 1 in my last filled P, which is 3 valence electrons. And picking up on this pattern, group 4 elements, main group elements, NS2 and P2, 2 in the last filled S and 2 in the last filled P, that is 4 valence electrons. Group 5, 6, 7, and 8. Just keep filling in those p orbitals, so that's ns2, np3, ns2, np4, ns2, np5, ns2, np6, respectively, which means we have 5 valence electrons, 6, 7, and lastly with our noble gases, 8. This is why these are not reactive. Typically unreactive, they already have achieved octet. So kind of knowing this just off the top of your head is going to be incredibly useful when we begin to draw Lewis dot structures. So for instance, draw the Lewis dot structure, LDS, my abbreviation, for the following atoms. So let's do hydrogen, let's do sodium, let's do barium, let's also do phosphorus, let's do bromine, let's do carbon, and I think that's a good sampling for now. So remember, anytime we're drawing a Lewis dot structure, we need to begin by drawing the element symbol and then placing our valence electrons around that element symbol, trying to abide by Hund's rules, where we place them singly around and then we go back and double pair, just because we're trying not to forget quantum mechanics. So here, this will be one valence electron because hydrogen is in our group 1, so NS1. So I'm going to draw 1 dot. Sodium, same group as hydrogen. So this also has only one valence electron. It's just a valence electron that's placed in some higher order or energy level s orbital. Okay, barium, Ba, that is here in group 2a. So if I wanted to draw these valence electrons, I would draw 1 and then 2. So again, taking care to draw them as far apart from one another as possible. I do not want to spin pair them before I have to. Phosphorus, P. So searching for phosphorus on the periodic table, we find it is here, group 5a. So this has 5 valence electrons. So I could draw 1, 2, 3, 4. And now let's go back. 5. Bromine. Let's find bromine on the periodic table. Bromine is one of our halogens, so group 7. That means it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Notice it's just 1 electron away from achieving octet. This is why these tend to form -1 anions. And then carbon, going back to our periodic table, carbon is here in our main group 4. So that means it has 4 valence electrons, drawing them in as such. There we go. These are the Lewis dot structures for these single atoms. What if we wanted to draw the Lewis dot structures for the above in their ionized state? So we've got hydrogen becoming H+, sodium becoming sodium+, barium becoming barium 2+. Again, I'm following the trend based on my number of valence electrons. If you would like, might as well throw it up on the board here. So our ionic charge is going to be inherently linked to our number of valence electrons. It's just a question of what is energetically more feasible. So these things have a +1 charge, group 2 +2. Over here, +3. This is where we're half at octet, so we can add electrons or lose electrons. And then we go to gaining, -3, -2, -1, 0. Okay, that was barium. Now I've got phosphorus. That is going to be phosphide anion. So that's going to have a -3 charge. I also have bromine, which is going to the bromide charge, which have a -1. It is a halogen. And then I've got carbon, and typically carbon doesn't ionize, but let's suppose we were looking at the carbon 4+ cation. And when I say typically carbon doesn't ionize, I mean we can force it to, but it would much rather form covalent bonds than it would ionize. That's basically all of organic chemistry, by the way. Okay, so if hydrogen had a Lewis structure with 1 valence electron, then the hydrogen plus cation would have to show the removal of that 1 electron And so it would have valence electrons being none. So if this is the ion, we have to show the removal of that one electron, and this would be our Lewis dot structure. Same deal for sodium. Sodium had one valence electron. So if I were to remove that electron, I would simply be left with my sodium element symbol. And again, I removed one electron because I'm a +1 cation. So here is our Lewis dot structure for this ion. Barium. So when barium is unionized or neutral, it has two valence electrons. But then if we were to become the Ba2 plus cation, this means we have to lose two electrons. So to get rid of those two valence electrons in our Lewis dot structure, we would just be left with the element symbol of barium, Ba. Okay, let's look at some anions now. So let's go ahead and change this to the carboanion, C-4. So phosphorus in its unionized state had 1, 2, 3, 4, 5 valence electrons. And if I wanted to make this phosphorus ion that has a -3 charge, I would have to gain 3 extra electrons. So then the phosphide anion would have its original 5 valence electrons with 3 being added so that this meets octet. And this would be the Lewis dot structure for the phosphide ion. That's a -3 charge. Okay, bromine, one of our halogens, has 7 valence electrons. And if I were to create the bromide anion, which has a -1 charge, then I would need to add an extra electron. So I would have my original atomic Lewis dot, which contained my 7 valence electrons, and then my extra. This creates the bromide anion Lewis dot structure. Notice we have 2, 4, 6, 8 electrons, so we've achieved octet. And then for carbon, when unionized carbon has 1, 2, 3, 4 valence electrons, it's halfway to octet. That's why we can either lose those 4 and become a cation, or gain 4 more and become an anion. So in the case of becoming the C4- anion, I would have my original 4 valence electrons, and then to become a -4 charge, I need to fully take in or accept 4 new electrons, and this would be the Lewis dot structure of the carbide anion. So notice, all of these meet octet. Well, duet here in hydrogen's case, but in the sodium plus cation, we have taken that 3s electron away, leaving behind our core electrons, which was that configuration of neon. And remember, neon is a noble gas, so it has 8 valence electrons. We could follow the same pattern here for barium. And then we can count visually just by looking at how we added electrons, 2, 4, 6, 8 in phosphorus, 2, 4, 6, 8 in bromine, 2, 4, 6, 8 in carbon. So all of these have also achieved octet upon becoming ionized. So if I were to draw the Lewis dot structure for an ionic compound, let's specifically do sodium bromide, I would start by looking at the electron configuration for sodium and the electron configuration for bromine. These are their unionized not electron configuration, number of valence electrons. So my 3s1 electron, valence electron on sodium, and then I believe bromine is 4p5, so 4s2, 4p5. And if I wanted to draw the Lewis dot structure for the ionic compound that forms when sodium and bromine come together, then I would need to recognize that in order for there to be an ionic compound and thus an ionic bond, these things need to become ions. And by inspection, or just looking, I can see that this sodium is willing to give up an electron to the bromine, which is willing to take it in. In doing so, we will be left behind with the sodium cation that has, let's see here, prior filled 2s2, 2p6. And then I would have the bromine anion, which had its original 7 valence electrons plus the extra that it took from sodium, now having valence configuration of 4s2, 4p6. And if I were to count my number of valence electrons upon the formation of this ionic compound, I would have achieved octet in the sodium and octet in my bromine. So this is how we would write our Lewis dot structure for our ionic compound, and then we would indicate our charges in little circles here, just to indicate like this is the kind of ion that was formed. And namely, remember, it is the ionic attraction or electrostatic attraction that exists between these opposite charges that forms what we call ionic bonds. This itself is the ionic bond. So as long as you're comfortable navigating the periodic table or recognizing the inherent periodicity of each of our groups based on our valence electron configuration, you will always be able to tell things like we mentioned last week, our ionic charge, and also now in our Lewis dot structure practice, the total number of valence electrons that each of these elements possess. So in our next video, we are going to start building covalent compounds. So we looked at how we can write the Lewis dot structures for atoms, simple monoatomic single atom ions, and also ionic compounds where electrons are either donated or accepted. Now we're going to look at how we would do this for covalent compounds in which valence electrons are shared.